on Tuesday. Do our quiz 6 on Tuesday on Lewis structures, and I'll have to go through the questions and see if I can find some good multiple choice type ones like what we practiced yesterday. We'll do that and just do it online. If I don't like them, then or I don't want to bother writing all that, then we'll just do an old-fashioned paper and pencil kind of quiz, so you can draw Lewis structures and draw all the stuff that we're going to talk about today.
So is there math and chemistry?
There is, but it's not required. You'll notice that it says practice next to it. It's not counted in your score because of how annoying it is to draw the structures in their software. So please don't skip it because you have to still practice this stuff, but it's not going to be graded. So the point of that is if you'd rather do the homework the old-fashioned way with paper and pencil, it won't check your answers, but it'll go a whole lot faster than messing with the software. But if you want to mess with the software, mess with the software. I'm not going to count it either way, just because it's been such a problem in the past. Okay. All right, so to practice from yesterday, let's draw Lewis structure for the nitrate ion, NO3-. Everybody try to draw a Lewis structure. And if you're reading ahead a little bit, you'll find that there are actually 3 different possible Lewis structures that are all correct. So the idea here is that if we look at what everybody drew, we might find some variation. So everybody draw a Lewis structure, and then we'll see what you got. So remember, add up the valence electrons. Make sure you add 1 extra for the negative charge. Then set up the connections, and then fill the valences. Make sure all the atoms have octet. Just go over on and see what the structures are. Okay. All right, so I saw some that look like this. Right? That look like a couple of yours? Okay. But then I also saw some that looked a little bit different. Maybe they were kind of a different angle, that kind of thing. Those are always the same. But what if we put the double bond on the other side? Or, I think I saw one that looked like this, putting the double bond down like that. And then these are all ions, so we put the brackets in there. All right, these are all correct structures for nitrate ion. In fact, they're really equivalent structures, but they're not the same. If you could actually label the oxygen atoms at the atomic level, which you can using other isotopes, we could say, all right, well, those oxygen atoms are actually different atoms. So the double bond going to one versus the other, those are actually different molecules. So when this situation comes up, this is known as resonance, that there are basically multiple structures, multiple correct Lewis structures that only differ by where the kind of extra electrons go. So the connectivity is all still the same. The nitrogen's in the middle, the oxygens are on the outside. They're connected. Nitrogen's connected to the oxygen. Oxygen's not connected to each other. But those extra electrons, whether they're non-bonding or whether they're put in as a double bond, those can kind of be in some different places. And those different structures are called resonance structures. We draw them with a double-headed arrow in between them. Now that name comes from the original theory of what was happening here, which when this was first kind of discovered or thought about, what the scientists thought was that this was actually resonating. Resonating meaning moving back and forth. So it was like switching really, really fast from that one to that one to that one to that one, back and forth, switching between all the resonance forms. We know now that's not actually true. It's not really switching. What's really happening is that in reality, the actual structure is an average of the resonance structures. So if you look at nitrate ion through some kind of spectroscopy, one thing you can do is you can measure the bonds. You can measure if they're single, double, or triple bonds based on bond length and some other stuff. If one of those structures were true, were the actual structure, or if it were switching back and forth, we would expect to see one double bond and two single bonds, right? But if you actually measure this, what you find is 3 equivalent bonds. All 3 of those bonds, those NO bonds in nitrate, are the same length, and they're about 1 1/3 of a bond. So that's what it means by an average of those 3 structures. If you average that out, instead of a double bond and 2 single bonds, the average is 3 1 1/3 bonds, whatever that means. It's not like a real thing, but that's basically what we see. So we can use the resonance forms and we can draw the resonance structures to help explain what the real average structure would be, which we call the resonance hybrid. And this is especially important in organic chemistry. So if you go on to do that, you'll spend a lot of time dealing with resonance structures because you can learn a lot about the reactivity and the behavior of organic molecules through looking at resonance structures. So we're going to look at them based on our inorganic molecules that we've been dealing with for the most part for Lewis structures. Well, let's look at the nitrite anion, NO2 minus. And so if we want to describe the electron arrangement, notice how that question is worded. Describing the electron arrangement means we want to know the structure, the Lewis structure, and we want to know where the lone pairs are, the double bonds, that kind of thing. So just as we did with NO3, see if you can do it with NO2. And then this time, try to find all the resonance structures. So see if there are different possible ways to arrange the electrons and write those down. We'll call those resonance structures. All right, how many resonance structures did you find? 2? Anybody find more than 2? Anybody only find 1? Are you still working? How many did you find? Are you still working? Okay, I got 2 so far. All right, take another minute and we'll look at those 2. All right, so I find these 2. Do you get something look like that? So those are resonance forms. Okay, so it's got 2 resonance forms, which means the overall structure, to describe it, we would really say that the nitrogen-oxygen bonds are equivalent, about 1.5 bonds. This is really important when we start looking at things like polarity. We talked about electronegativity differences in bonds, right? That's going to come up on the exam. If you imagine this structure, and it's actually bent, but either way, if it were really a double bond and a single bond, that would be kind of asymmetric. And that would change the polarity. That would change the dipole moment. Because it's an average of the 2 resonance structures, it's actually totally symmetric. And so its polarity is going to look just like water, rather than kind of this lopsidedness. So resonance helps us understand what the overall hybrid structure would be. Okay, let's look at another one. This was one from the thing yesterday that we did. A Lewis structure for ClCN. It's not CICN, ClCN. So chloride, chlorine, carbon, nitrogen. See if you can draw 2 resonance forms for this Lewis structure. Actually 3. There should be 3 Lewis structures that you can draw that have the same connectivity, the same everything fits the octet rule, but different double bonds and lone pairs distributed. So find 3 resonance forms. You have 1, so you can move those electrons around and the other ones. Anybody find all three resonance structures? Everybody got one structure? You think looks good? All right, let's look at the one structure. And go from there. So somebody want to just describe what one of your structures looks like? Or you can come up and draw it if you don't want to describe it. That's fine. You got one. What does yours look like?
That's a C in the middle.
Mm-hmm.
And two double bonds on there.
So one going to the right and one going to the left?
Yeah.
Like that?
So,
Okay. And what about the electrons? Just filled in appropriately. So two here, two pairs there, and two pairs there. All right, anybody else get a structure like that? Cool. All right, did anybody get a different structure? Yeah.
So I had CL and then C and N. And then for the CL I had 3. And then 1 on the end and then 2 on top of the end. And then 3 around the CL. Or
Like that?
Yeah.
Because CL would be
Yeah.
would violate the octet if we did that, right? Okay. Anybody get another one? Same thing on the other side. Like that? Yeah. So there's the three structures. Let's talk about how we get there if we get one of them. And then we'll talk about how to judge those structures. So these, you probably believe me when I tell you, these are not equivalent structures. They are different. It's not like the NO2 with the double bond on one versus the other. Yeah.
Well, isn't that not an ion?
Oh, yes, thank you. Sorry. Just got in the habit from the last part. No, you're right. This is not an ion. It's neutral. Okay. So these are not the same. These are not the same. Which makes sense. I mean, a triple bond between C and Cl has got to be different from a triple bond between C and N. It's not like when there's an oxygen on each side. So we'll talk in a minute about formal charge, and that's how we judge which of these is better. But how, let's say we found that first one, how would we go about finding the other ones? One useful technique is the way we do it in organic chemistry, where we imagine a kind of a systematic way of moving the electrons around. And we draw that with little curved arrows, an arrow showing where the electrons are going. So we might say, okay, well, we've got this one with these two double bonds. What if we take one of these pairs of electrons and we put it down here to form a bond? Well, if we did that, sorry, you can't see my finger pointing at the screen. I always forget about that. If we put that here, now this carbon would have too many electrons. Everybody see that? It would have 10 instead of 8. So we need to kind of release one of these to make room for it. It's almost like it pushes the other one out of the way because it's already full. So if we push this one out of the way, it jumps over to the nitrogen, and that's how we get this one. We could imagine that happening kind of twice, going back the other way then to form this one. But that's one way to find other resonance structures. If you can only find one, or you can only find two, or you're worried if there's more. Imagine all the free pairs of electrons falling down into bonds, and then what would have to do to compensate for that. And if you keep kind of moving things around the molecule, you'll find the other resonance forms. All right, so how do we judge these? How do we decide what's a better resonance form? We're going to look at the stability of these, the overall stability of the molecule. And the way that we look at that is something called formal charge. We talked about overall charge. You know, you put the brackets on, you got a little charge. That's for the overall molecule. But we can actually kind of use this technique to go right down to the atomic level and decide where are the charges actually located on the ions. Where are they localized, rather than over the whole molecule. Now, that doesn't mean that in the actual structure there's a charge on that atom. That's why it's called formal charge. It's like a form to use to help us understand it. So we're going to calculate formal charge for each atom in a Lewis structure. And then we're going to look at how to minimize that. So let's look at SO4. sulfate ion, SO4 2 minus. That is, let's see, sulfur is 6 and oxygen 6, so that's 30 electrons total, plus 2 for the 2 minus. So we've got 32 electrons to deal with in the structure. As usual, we put our sulfur in the middle, our oxygen's all around. That takes up 8 electrons, and we've got to get up to 32. So 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. Okay, then we check our octets. Everything looks good, right? Everything has an octet there. You can count 8 electrons on each atom. So we're good. We put our brackets in. We've got a structure for sulfate ion. Okay, and yes, that's a Lewis structure for sulfate ion. That's fine. Now, we're going to calculate the formal charge for each atom in sulfate ion. And to do that, we take the number of valence electrons of just that atom. We subtract the number of non-bonding electrons we see on the atom, and then we subtract the number of bonds. So for this oxygen right here, our formal charge is going to be, we start with 6 valence electrons, right? Oxygen has 6 valence electrons. Then we subtract the number of non-bonding electrons, which is 6. And then the number of bonds, which is 1. There's 1 bond going to that oxygen. Does anybody not see where those numbers come from? Okay. We do that, we get -1. Yeah. We're using this formula right here. So we've got the number of valence electrons, which is 6. Subtract the number of non-bonding electrons, which is 6. 1, 2, 3, 4, 5, 6. And then subtract the number of bonds, which is 1. Just this one. So 6 minus 6 minus 1 is -1. So we would say that that oxygen atom has a formal charge of -1. And the way that we express that is by putting a negative sign in a circle. Sometimes the negative sign doesn't have a circle. As long as you make it clear, it doesn't really matter. So there's a negative formal charge on that oxygen. Now, you could probably see that the remaining 3 oxygens are all going to have the same formal charge as that one, because they're all in the same situation. They're all oxygen. They all have 3 pairs of non-bonding electrons and 1 bond. So we can just put negative formal charges on all those oxygens. And then the other one we have to calculate is sulfur. So the formal charge on sulfur, 6 valence electrons, no non-bonding electrons, and 4 bonds, is +2. So we're going to put a +2 formal charge on sulfur. Okay. So that's the formal charges, and that's not great. Generally, when we draw good Lewis structures, we want to minimize the formal charges. Ideally, have no formal charges at all. Have everything be 0. So the fact that there are 4 -1 charges and 1 +2 charge tells us that we can do a little bit better job, that we can find a better Lewis structure, that this is not the best resonance form for this ion. So how could we draw a different resonance form for this ion? Yeah, we could put double bonds between the oxygen and the sulfur, because sulfur is in the 3rd row, which means it's fine with having more than an octet. So if we put, let's say, we make 2 of these into double bonds. Okay. Now these oxygens on the top and bottom are still looking the same. So those are still going to be -1. Now let's calculate the charges on the remaining oxygens and sulfur. So this one is going to be 6 minus 4 minus 2, 0. And so that other one's going to be 0 too. And when there's 0, we don't put anything on there. You don't put a 0 there. You just leave it as is. And then the sulfur in here now, as you can probably see, no non-bonding electrons, 6 bonds, gives us 0. So far fewer formal charges on this structure now. And then that's good. That helps us. Now, we can't get rid of the formal charge entirely, because one of the rules of formal charge, I'll just write it down here, is that the sum of the formal charges must equal the overall charge. So if this is an overall 2 minus ion, then all the formal charges must add up to be minus 2, which means we'll never actually get rid of formal charges in an ion. But that's better than the other one. All right. So let's go back to, well, here, a couple other things. A couple other things about judging formal charges. So generally, we want to minimize the formal charges. We want the lowest formal charges, the fewest we can with the lowest charge. In general, any formal charge more than plus or minus 1 is really not great. So if you have a plus 2 or minus 2, that's probably not a great structure. And then finally, negative formal charges are more stable on more electronegative atoms. So going back up to this example, if we put 2 more double bonds, so we had 4 double bonds instead of just 2, that would also lower our formal charges in that all the oxygens would be neutral, and the sulfur would have a formal charge of minus 2. But that's actually a worse structure because oxygen can better stabilize that formal charge than sulfur, because oxygen is a lot more electronegative. So that's a lot. We'll use that a lot in judging these structures. So let's go back up to what we looked at before. All right, we've got these 3 structures for ClCN. I want you to calculate the Lewis or the formal charge for each atom in each structure, and then decide which one you think is the better structure. I don't know if I can get the formula on. Yeah, I can't get the formula on that same screen. I'll put it up here. Remember, formal charge is the valence electrons minus the non-bonding electrons minus the bonds. And you need to know that formula. All right, got some formal charges? Keep working on it. I'll give you another minute. I'll start filling this in. To do something like that? So what's the best Lewis structure? The third one, right. Which means that if we look at the structure, if we had a sample of it and we were analyzing it and measuring it, it would be likely that the average structure was pretty much just that structure. It's unlikely that these two resonance forms really contribute strongly to that hybrid. That hybrid or average structure would really be more just like this. So it's not really a true average, it's really a weighted average. Whatever the more stable resonance structures are, contribute more to the average. Like that middle one is completely not going to be really contributing. That's not really it's not really stable at all. So that tells us that there's really not going to be any triple bond type character between the Cl and the C in the actual structure. It's going to be mostly like a triple bond, a single bond, and then a triple bond between C and N. So the resonance structures can help us to judge that. All right. Let's try another practice. Oops, it's Isomers. And when you do things like the exams, which are mostly multiple choice, rather than asking you to draw the different resonance structures, it might just ask you to find the best structure. To find the best structure, you really have to draw the resonance structures, do the formal charges, and then figure out which one's going to be the most stable. So try that. You should be able to find 3 resonance structures for isocyanate, and then choose the best one. Choose the one that you think is the real structure. All right, got some structures here. So yours might be in a different order, but I find these. What do you think? We're good? Do you get some of those? Maybe? Maybe not? Maybe a little? Yeah, so those are the three resonance structures. And you'll notice they differ in where the bonds are and in the formal charges. From this point forward, a Lewis structure is not considered correct if it's missing formal charges. So yesterday we drew some Lewis structures and we didn't put the formal charges in because we didn't talk about it. But now that's considered a part of the Lewis structure. So your Lewis structure is not complete without the correct formal charges on there. The non-zero formal charges. You don't have to put all the zeros in. So looking at those formal charges, which is the better structure? Which is the best structure? There's no easy winner where it's just all neutral. Everything has at least one charge because it's an ion. So where is the best place to put that negative charge?
The last one.
The last one, right? Why?
Because the oxygen is most electronegative.
Yeah, oxygen is most electronegative, so that's going to be best at stabilizing that negative charge. So that makes this one the best structure. What's going to be the worst structure? The first one, why?
Because the electronegative charge is on the nitrogen and it's -2.
Yeah, it's got the biggest charges. It's got -2. It's got 0. It's got another one over there. So it's got more formal charges, more positive or more negative formal charges, and on the wrong atom. So that's definitely going to be the worst. And this one's kind of in the middle, right? So that tells us that in this overall structure, we would expect the one on the right to be the most contributing to the overall structure, meaning that we would expect the oxygen to be kind of have most of that negative charge. We would expect that CN bond to be pretty much a triple bond, and then the middle one may also contribute a little bit. So that CN bond may not be fully triple; it might be like partway between a double and a triple, but more toward the triple. So you judge the stability of the resonance forms, and that tells you about the overall structure, which then also is going to affect how we expect it to react and how we expect it to behave in other ways. So please practice this. One of the biggest things with doing formal charges especially, obviously we just started it, and it's pretty annoying because you have to calculate it for every atom all the time when you do these structures. But if you practice and you draw a bunch of Lewis structures and you're calculating formal charges all the time, you just sort of get used to it. And you notice, okay, anytime an O has one bond, it's going to have a -1 formal charge. Anytime an N only has one bond, it's going to have a -2 formal charge. You just get used to these things from seeing them over and over and over again. And that makes it a lot faster come exam time, so you don't have to sit there and calculate formal charge for every little atom all the time on all these structures. You just kind of can look at it and say, oh yeah, that's how it's supposed to go. So please practice this. Please work out the homework for that. All right, we're going to stop there because I want to make sure to have time. You can practice this one as well on your own, xenon trioxide. And then there's a little bit more to this chapter about bond energies and enthalpies. We'll talk about that on Tuesday, so that won't be on the quiz, but it's just a little bit. So the exam tomorrow will not have any of this stuff. The quiz on Tuesday will be on drawing Lewis structures, resonance forms, formal charges, and then judging those. All right, so what do you want to talk about now? What's been bugging you? What kind of problems have you been getting wrong in your practice and review and stuff for the exam? If everybody's in good shape, that's fine. But this is the time. If you got questions, you should ask. Yeah.
Not related to the exam, but on the last problem we just did, why would the last one be less structured? Like,
The last one's the best structure because the more electronegative atom, oxygen, has the negative formal charge. So we want, and it doesn't necessarily work the other way, which is why we say it this way, but we want the more electronegative atom to have the negative charge. So between that one and the middle one, the one on the right is better because on the one on the left or the one in the middle, the nitrogen has the negative charge instead of the oxygen. And I think that was on this. Oh, yeah. So I guess as long as we're talking about this, there was one other question on the thing yesterday that deals with this. So N2H4 hydrazine, the correct answer was the best Lewis structure is this one. But how do you know that it's not this one? There was one other one that is also correct in terms of a Lewis structure. So how would you know that it is not as good of a structure? And the reason is when you look at the formal charges, the structure on the left has no formal charges. The one on the right, if we calculate it, this nitrogen is going to have a formal positive charge, and this one's going to be a negative charge. Are those resonance forms? They're not. The reason they're not resonance forms is that they have different, what we say, connectivity. Things are connected in different ways. So there's a word for that too. They're called isomers. Same formula, but connected in a different way. Resonance structures have to be connected in the same way, just differ by how the electrons are arranged in the structure, like double bonds over here versus over here, or lone pairs here versus over here. So if you do get to these, drawing some of these structures and you're not sure how to make them connected, try one, calculate the formal charges, and then if you get a bunch of charges, chances are there's a better way to do it. Anybody find any exam type stuff to ask about yet? Yeah. Those will always be there. I mean, there's not going to be a bunch of questions that are like, what is phosphate ion or something, but you need to know that to be able to answer other things. Yeah. Yeah, being able to draw formulas from names is always going to be a big part of the exams. Just stare at each other for 25 more minutes. Anybody else find anything? Yeah. Yeah, let's look at oxidation numbers. As you mentioned that, this won't be an issue on the exam, but generally oxidation number gets confused with formal charge sometimes. It's not the same thing. Formal charge is an accounting of kind of where the electrons are in a Lewis structure, which is different from oxidation number. All right, so there's a couple ways to calculate oxidation number. One is when you just have ions. An ion has the same oxidation number as its charge. So if you had something like FeCl3, what's the oxidation state of iron? What's the charge on iron? Close, yeah, +3. It's got to be +3 because there's 3 chlorides in this compound. Each chloride is -1, so you need +3 on the iron to offset the 3 -1s. So that means that the oxidation state is also +3, 3+. That's always how it is for ions. Where oxidation state can get a little bit trickier is in covalent compounds when it's not as straightforward. So let's take something like nitrate ion. We want to find the oxidation state of nitrogen. And to do that, we have to look at the molecule and how do we figure out the oxidation state of nitrogen in the nitrate ion? Yeah, we use ones that are more common in a particular state. So we know oxygen is almost always -2, except if it's an elemental oxygen, or the other exception is peroxide, but it's pretty much always -2. So if oxygen is -2, there's 3 of them, that's -6 overall. We want a -1 charge total. So what does nitrogen have to be? +5, right? So we would say the nitrogen's oxidation state there is +5. So you use the elements you know to find the ones that you don't. Methane, CH4. What's the oxidation state of carbon? Yeah, this one's going to be -4 because the hydrogen is usually +1. And so if the hydrogen is +1, there's 4 of them, then carbon has to be -4 to offset that. See you tomorrow. Happy studying. What else we got?
Is there anything on the review package that will be on the?
Let's take a look.